Hello, everyone. Welcome to the C2 Smart webinar series. I'm John Patinos, the project manager here at C2 Smart. As a heads up, this webinar, like our others, will be recorded and uploaded to the C2 Smart YouTube channel. We will have time for some questions today. If you have anything you'd like to ask today's presenter, you can feel free to type the questions in the Q&A box at the bottom of the screen, and I will read them out loud at the end of the webinar. So today I'm happy to introduce Dr. Bekir Bartin, full-time associate professor in the civil engineering department at Özyeğin University in Istanbul. Prior to his current position, he was the founding chair of the civil engineering department at Attinbas University, if I said that correctly.
That's correct.
All right, good. Dr. Bartin worked as a full-time research associate at Rutgers from 2006 to 2012, where he conducted research projects, supervised graduate students, and taught courses. His research interests lie in transportation systems, application of reinforcement learning methods in traffic simulation, economic evaluation of transportation investment projects, traffic safety, and security. He served as a principal and co-PI of more than 20 projects, and he is a research affiliate at C2 Smart. So today he's going to be presenting his work with New Jersey Department of Transportation, NJDOT. Shout out to NJDOT. His work is called Calibration and Development of Safety Performance Functions for New Jersey. Dr. Bartin, please take it away.
My name is Bekir Bartin, and the title of this presentation is Calibration and Development of Safety Performance Functions for New Jersey, which happens to be the title of the NJDOT research project that we completed back in October 2019. And our team members are Professor Kaan Azbey from C2 Smart at NYU, Professor Hani Nasif from Rutgers, Dr. Chuan Xu, who was a visiting scientist from China, and also our friend and colleague Abi from NYU. Before I get to the objectives of this research project that we completed, and ultimately the objectives of this webinar, I would like to spend a couple of slides explaining the HSM procedure. HSM, first published back in 2010, it provides a comprehensive approach for roadway safety analysis, and its predictive methods are based on safety performance functions, SPF for short, and these are regression models that correlate the number of crashes, average number of crash at a given site with different covariates such as traffic volume, AADT, geometric and operational characteristics, for instance, the number of lanes, lane width, shoulder width, if it is divided or undivided roadway, and so on and so forth. And the HSM provides SPFs for either roadway segments or intersections for specific base conditions, which I will get to that in a couple of slides. And the generic form of SPFs are quite simple, as you can see, for roadway segments and intersections. And for roadway segments, we have AADT and roadway length. And for intersections, we have the AADT on the major and minor approaches separately, and A, B, C, D, and E are model parameters, and they change for different facility types. Now, these SPFs given in the HSM, they were developed with data collected from various states in the United States, and because of that, they cannot be simply used at other states or other locations, and to better accommodate local data, there are two ways to do that. The first is either to calibrate the SPFs given in the HSM, and the second one is to develop new SPFs using jurisdiction-specific data. And the first edition included 3 different facilities. These are 2-lane, 2-way undivided rural roads, and multi-lane divided and undivided rural roads, and urban and suburban arterials. The second edition, I believe it was 2014, included freeway segments and ramps and freeway terminals. And the objective of the completed project was to either calibrate SPFs or develop new ones using NJ-specific data. Now, it sounds quite simple of an objective. However, there are certain caveats. First, either roadway segments intersections should be identified, which is not as simple as it sounds. First of all, we have to define homogeneous roadway segments. By homogeneous, I mean, or the HSM means, every geometric detail is exactly the same within the segment, meaning the number of lanes is the same, lane width, shoulder width, everything is the same. And there are different types of intersections, four-way, signalized, unsignalized, three-way, signalized, unsignalized intersections, and we have to find that out. And this requires a significant data processing effort and requires computer programming, which I will explain it in detail in the upcoming slides. The second one is whether it is calibration or development. SPFs require, this is a very highly data-driven process. And the data required can be classified into three major groups: AADT, traffic volume data, roadway geometric features, and also crash data. And there are the data required. There are either required data or desired data by the HSM, and there are 76 unique variables data needed, and 47 of them are required, and the rest of them are desirable. And the majority of the required variables are roadway geometry data. Now, collecting or extracting these data is very time-consuming and labor-intensive, and because of that, it is very important to automatically acquire as much data as possible from existing databases. And unfortunately, as stated in the literature and also in our research report, is that the readily available roadway databases, inventory databases, are not really up to standards. They do not include all the data required by the HSM. So there is always some manual data required. The objectives of this webinar is I would like to show the development and calibration results, but not for all the facility types. I want to focus on the rural two-way segments and intersections. And most importantly, I want to show the data processing methods and approaches to gather the required data for calibration development. So we have so many different databases to put them in a unified format. It requires a lot of effort. And the key takeaways is what I want to get to is that no matter how good your database you think, no matter how good your database you think it is, they're hardly ever free of errors and inconsistencies. And generating a usable data set from various sources requires a significant programming effort. And unfortunately, manual data extraction is always needed, as I said before, no matter how comprehensive the database is. And therefore, although we have to spend time for manual data extraction, perhaps we can find novel data extraction methods and minimize the time for this process and increase its accuracy, for instance, using machine learning methods. Now, let me give you a brief background on calibration and development process. First, calibration. And calibration is simply, if you can just skip to this formula, we have this calibration factor is the number of observed crashes at a given facility type. For instance, let's say you're looking at a four-way signalized intersection on rural two-lane roadways. Okay? And we have to use 30 to 50 samples of the same facility and look at the number of crashes for all those samples, divided by the number of estimated ones. Number of estimated comes from the HSM, observed comes from the crash database. For instance, so I want to show you how we can calculate the estimated one. It comes from the HSM. So the SPFs in the HSM, as I said before, it gives us the average number of crashes for specific base conditions. Now imagine that in our example, we're using four-way signalized intersection, and we went out and collected 1, 2, 3, all the way up to K a number of different intersections in New Jersey. And then we extracted their AADT for the major approach, for the minor approach, lane width, skew, lighting, for all of those required or desired data. If I want to calculate the number of estimated crashes, it is equal to the base one. This is in the previous slides I showed the generic form of the SPF, specific for base conditions. If any of these deviate from the base conditions, we multiply it with the crash modification factors, and these are all given in the HSM. So I find the estimated number of crashes per year for this intersection, and I do the same thing for the second one, for the third one, all the way up to the kth one. Okay? And for these sample intersections, I find the total number of estimated average crashes. And using the formula that I presented in the previous slide, I can find out the calibration factor using this simple ratio. So it is just a simple ratio. Whatever we get from the HSM, we either increase it or decrease it using our sample facilities that we extracted. So this is the calibration part. If one wants to develop jurisdiction-specific SPFs, so we need to find out a functional form that correlates the number of crashes with different covariates. So in this case, we cannot use linear regression because, first of all, the number of crashes are always integers, they're whole numbers, and also they can never be negative. The lowest possible value is 0, and they're always positively skewed, like the one that we can see in the graph here. The most common type of distribution for crash counts is a Poisson distribution. It is defined by a single parameter mu. In this case, mu is the base crash frequency. So we want to equate this, we want to correlate this by using different covariates such as AET, lane width, and so forth. So if we just using basic calculus, we can just convert this to the same functional form that I presented earlier. However, the problem is Poisson distribution assumes that the mean and the variance of the variable are equal, which rarely holds in reality, because variance is much larger than the mean. This is called over dispersion. Therefore, a negative binomial regression approach is used to overcome this issue, and this is the same approach used in the HSM to develop these SPFs. And now alpha here is the dispersion parameter, which is very useful in empirical bias method. Now, how do we do the development? Obviously, we're using the similar type of database used for calibration methods. For instance, the same thing, we have the AADT, lane width, and all the other traits for the facility at hand. So this is the first covariate, second, third covariates, and then we try to come up with a function that correlates the number of crashes with the covariates. Now, what HSM does is that it puts a certain value for instance, if this is the lane width, it puts a lane, a 12-foot lane, and for instance, 6-foot shoulder width, and then makes it a more simplistic and a concise functional form. So this is the base form. So as I said before, if any of the covariates, for instance, the lane width or the lighting or the skew deviates from these base conditions, we have to multiply with the CMF. And let me get to the data requirements, specifically for the rural two-lane, two-way roadways, R2 for short in this case. And for the segments, we have the segment length, ADT, curve length, curve radius, and there's so many of them either required or desirable. Okay? And I'm also demonstrating whether they are available from the readily available databases or it was extracted, and I'll get to these in the upcoming slides. And for the intersections, we have, for instance, the ADT for the major road, minor road, skew angle, and the number of approaches with left turn, right turn lanes, or whether lighting is present or not. And the available data sources for this specific project. So the data sets, data sources we have can be categorized into three classes. We have first traffic volume data. The first one is from detector counts from either permanent stations or temporary stations, detector stations. And the second one is the turning movement counts at intersections in New Jersey. And the second data set is roadway features data. And we're using the straight line diagrams, 2017 edition, and we also use the New Jersey GIS, centerline GIS map. And the third one is the crash data, and although we have a very rich crash database, which is also available, this is a raw crash database. The other one is the Voyager safety data. This is the one that we utilize the most. Now, before I get to anything, I wanted to show you the overall procedure. So we have the roadway features data. In order to, and this is the overall procedure for the R2, meaning the rural two-lane roadways. In order to find out the roadway segments and intersections by type, first because we're dealing with the rural roadways, we are using the urbanization code and just get rid of the ones that are urban and only deal with the rural ones, and also filter out the divided roadways because we're interested in undivided roadways. And then we're looking at two-lane roadways and dismiss anything that has more than two lanes. By the way, when I say 2 lanes, it's 2 lanes total. So one direction and 1 lane for each direction. And then we have the segmentation process, which is the hardest one because we want to find out the homogeneous segments. First, we split at each intersection, split at curvature when there is curvature, median type when median type changes, median width changes, shoulder width changes, pavement width changes. We cut it down, and then we try to find out the homogeneous segments. Now, at this point, once we split at intersections, we also look at the intersection type, whether it is 3-leg, 4-leg intersections, or whether they're signalized or stop controlled. And then we find out our 2 segments intersections by type, and then we gather the required geometric and operational features data. If there's anything missing that we cannot find in the existing database, we try to extract this data manually. And the most common method is Google Street View, Google Maps Street View, or Google Earth aerial images. And then once we get every required geometric and operational features data, then we have to assign crash and traffic volume data. So they come from the traffic volume database and the crash database. And then we have a readily available database, roadway segments and intersections. And we have the crash data available. We have the traffic volume data available. We have all the geometric features available. So we have the crash data and all the covariates. So we can, the decision boils down to, do we calibrate or do we develop SPFs? So there are advantages and disadvantages for calibration and development. And what turns out that actually the amount of data required for both, although we require more to develop SPFs, the amount of struggle that you go through is almost equivalent. There is unfortunately little guidance in the HSM for SPF development. But there are certain guidelines for calibration, which I mentioned before. It requires 30 to 50 sites and at least 100 crashes per year. And crash data requires only at least 3 years of crash data. And for development, obviously, we need more number of data samples. And our diagnosis, our decision is because, as I said before, the trouble that you go through to find out that final data set, combining data from different sources, getting the crash data, everything ready, is almost the same. So we said that if we have the number of required data size for development, we'll just develop the SPFs and also calibrate it. But if you don't have it, if you don't have enough data, then we'll just calibrate the SPFs. So However, as I said before, there's very little guidance in the HSM for SPF development. So if we remember this from the previous slides, what HSM recommends is to develop this base SPF, meaning the function that gives the average number of crashes for certain base conditions. However, we did this for instance, for this specific R2 segments. Out of nearly 6,000 data samples we had, only 28 of them had the base condition. So you cannot really develop anything. So what we did is we used so we actually developed the N estimated SPFs here. Now, the next step is data processing. So we have all the data available. I want to talk about the roadway features data, traffic volume, and crash data. And first, the roadway features database. We use, as I said before, 2017 straight line diagrams. And it includes in various tables in access format for different geometric and operational features for New Jersey roadways. And the other one is the New Jersey JS database. However, there are certain issues observed in the straight line diagrams database. The most common types of errors were some of the intersections, some of the overpasses were identified and coded as intersections. And there's some missing data such as the lighting information. And there are some other errors that we find out, not very common, but it included incorrect number of lanes, payment width, and parking information. And also it does not include the number of left and right turn lanes at intersections, which are required data for intersections for R2 roadways. So in order to complement their information, we used Google Maps and then Google Earth and Google Maps, and then we checked whether it's an overpass or not, validated the number of lanes and number of legs, and then we went into the street view and then find out if there's a light present, whether it is signalized or not, if there's a no turn on red indication, and so on and so forth, the other things required or desired by the HSM. And there are two crucial issues in the processing of roadway feature database. The first is the identification of intersections by type, and the second one is the horizontal curvature information such as curve radius and length. The first one is intersections and identifying the intersections by type. In order to do that in the straight line diagrams, and there are two separate tables. One is PT intersection, the other one is PT INT approach table. Now, these are, for instance, the one includes the SRI and milepost, the other one includes latitude and longitude of the readings of the intersection. One includes skew angle, the other one does not. So none of them have the complete information. So we had to combine them to get a good idea of what the intersection database looks like. So the common drawback, so after we kind of merge them together, the common drawback is that especially for the three-way intersection, it cannot identify when the roadway is divided. So you can see this here in this figure, and when the roadway is divided, the three-way intersection can be either like this or like this. So what we want is, this is the two-directional three-way intersection which we want. We have to dismiss these, because if there is a crash here, that crash is not due to the intersection. However, if there's a crash in the two-directional three-way intersection, it is due to the intersection. So we have to get rid of these. So we used to correctly identify the type and location of the intersections. We developed a C programming code that processes both tables and then makes use of the GIS links database to determine whether it's a one-direction or two-directional intersections and dismiss the ones that are one-directional. Now, the major one is the horizontal curvature data. This is very hard to come by. We can look at the plan files and that are in PDF format, but they're not in usable format. So many studies in the literature, they conducted manual extraction of this data set using Google Earth images, which takes a very long amount of time, and it is very labor intensive. And unfortunately, even if you do that, it is prone to errors, especially in detecting and measuring the radius of compound curves. So what we decided is that instead of doing manual labor and spending months of extracting this data, we decided to extract this data using GIS center line map of New Jersey roadways. So we used a novel clustering-based approach. Actually, this is a topic of a later webinar that is scheduled for, I think, in November. So this clustering-based approach identifies horizontal curves using approximated curvature values of data points from GIS roadway centerline maps. So you can see this here. Any given roadway, we can find out the vertices, and then we can use the we can find out, we can approximate the curvature values of each point. And for this hypothetical roadway, for instance, when we divide this into vertices and then calculate or approximate their curvature values and draw it on a graph, you can clearly see the curvature values are can be clustered like this. This indicates there's a tangent section. This indicates there is a curvature section. This indicates here there's a tangent section. So if we can actually do this, calculate the curvature information for each node, and then do a clustering analysis, we can easily find out the curvature information. So to do that, we developed another C programming language which does the clustering, which uses a modified global k-means clustering algorithm. And then this program processes all rural roadways in New Jersey within 5 to 10 minutes. And then it gives us the location of the curvature, the radius, and the curve length for all the roadways in New Jersey. So we kind of put this into the available roadway features datasets, and could do this within a matter of minutes instead of spending a lot of time for manual data extraction. And the next one is the traffic volume database. As I said before, there are two sources of traffic volume. One comes from the detectors, either permanent or not, or weighing stations, WIM stations. And the second one is the turning movement counts. The AADT is a key variable in the crash predictive model of HSM, so we need to find that out. Unfortunately, it turns out it's not always possible to locate AADT, especially for rural intersections. So for each facility, whether it's a segment or intersection, the closest traffic count is determined based on the XY coordinates of the detector station. So when we find out the homogeneous segment or intersection, we try to find out on the same roadway the closest detector station available in the database. Now, there is certain data processing included, which is data cleaning. For instance, we had same station with different direction information or missing the ADT, and we merged the available traffic volume databases, and if we had ADT missing for a certain year, we interpolated or extrapolated as suggested by the HSM. And the as I said before, the second one was the turning movement counts, and these were given to us by the New Jersey Department of Transportation in comma delimited format, and it included 138 intersections, and unfortunately they were in not very usable format, even if it was in a comma delimited format. We wrote a C programming code, another one, that can read these data and then produce a summary of the ADT for major and minor approaches. And we also shared this information with the DOT, so which was a win-win for both parties. And the third class of data that is of interest to us for either calibration or development is the crash database. Now, crash coordinates is very important for assigning crashes two intersections. So we use so there is roadway segments and intersections. For roadway segments, milepost information is sufficient to determine whether it is within the crash is within the segment that we're interested in. For intersections, however, we need the crash coordinates to determine whether a crash is intersection related or not. One must define, as per the suggestion of the HSM, determine whether its location is within 250 feet of the intersection. So anything that is within that radius is considered as an intersection related crash. Anything else is a segment related crash. Now, here we cannot use milepost information because even just 1/10 of a mile is 128 feet, which is any inaccuracy in the location information will lead to incorrect assignment of the crash. As I said before, to assign crashes to segments, SRI and milepost information is just simply enough for us. Crash location, unfortunately, which is also reported in the literature and which we witnessed with the crash database that we were provided with, the SRI, meaning the roadway name, milepost, and travel direction is usually the most incomplete part of the crash database. It makes it very difficult, if not impossible, to get the accurate location of the database. In New Jersey, the police are they use GPS devices. They're supposed to use GPS devices. They can record crash coordinates and add it to the crash report. However, when we look at the raw crash database, it just the X and Y coordinates are the information included in the raw database is very low. It varies from 26 to 46%, which is not enough at all. So what NJDOT does is they post-process this raw crash database and geocode crashes with missing coordinates using roadway name, milepost, and cross street names. And they after this post-processing, nearly 95% of all the crashes have their X and Y coordinates. Now, after post-processing, however, although they have the X and Y coordinates, which is great for assigning crashes to intersections, most of them are still missing SRI and milepost information. You can see from this table from 2011 to 2015, nearly 95% of them have crash coordinates. However, nearly 50% of them have SRI and milepost information. There are many of them are missing this information, which we need them for assigning crashes to segments. So what we did again is using another programming code. We restored the missing roadway name and milepost information using the New Jersey GIS map. In the map, we have for each link we know the start and end milepost of each link, and also start and end milepost, start and end X and Y coordinates. So we can use that information to locate where the crash is, meaning using the crash's X and Y coordinate, we can assign its SRI and milepost information. Now the problem is that this is the crash data for 5 years is nearly 260 megabytes. There are many crashes, and also the GIS shapefile has nearly 500,000 links. So it took nearly 18 hours, but this was a one-time process. After that, we were able to restore and identify all missing SRI and milepost information for these crashes. However, at the end, we had a surprise, which I will get to that at the end of the presentation. Now, next is the SPF calibration and development. As I said before, I will only focus on the R2 intersections and segments. First, the intersections. There are three types of intersections for R2 roadways: three-way stop-controlled, four-way stop-controlled, and four-way signalized. There is no signalized three-way intersections in New Jersey in the HSM. Therefore, we don't have the calibration results, but we developed SPFs for that. The data required for the HSM, as a reminder, is ADT for major and minor roads, skew angle, number of left turn lanes, right turn lanes, and lighting. The base conditions are the intersection has to be perpendicular, zero skew angle, no left turn or right turn lanes, and there should not be any light present at the intersection. Any intersection that deviates from this, we multiply with the crash modification factors. At the end, so I'm showing you the preliminary data sample size and also the final sample size. The reason why it is lower is because this is the sample size we automatically found out using data processing methods. Once we looked at in detail one by one, we found out that, as I said before, some of them were actually overpasses, not intersections, and some of them were not actually two-lane, rather more. Whether it was not three-way or four-way, we just kind of move things around, and then at the end we had the final data sample size. For each of them, we have the average average ADT for the major approach, for the minor approach, and we also look at how far away the closest sensor station, detector station from the intersection. So average distance between the major intersection is 0.75 for this specific type of the intersection, and from the minor it is about 1.22. So it is, because it's a rural roadway, it is very it's not as easy to find out detector stations close to the intersections. And then we use the calibrator tool developed by the FHWA to calculate the calibration factors and also measure their goodness of fit. Our calibration factors were nearly 0.9, and you see the standard errors and coefficient of variation according to the FHWA report, which I am showing you the reference here at the footnote. The reasonable threshold for the calibration coefficient of variation has to be between the maximum of them has to be up to 0.10 or to 0.15. In that regard, we are good, except this four-way signalizing section a little higher than 0.15. Another way of looking at the validity of the calibration factor is the CURE plot, the cumulative residual plot. And this is simply the graph of cumulative residuals observed minus predicted crashes against a variable of interest. So the residuals between the estimated and observed values are assumed as independent random variables. They say these plots are based on a loose version of the central limit theorem, and we expect that if the calibration factor is good, the CURE plot should be within the expected limits of an unbiased random walk, plus and minus 2 standard deviations. And for those who are interested in CURE plus, the reference is given at the footnote here. Now we're looking at here, the blue is our CURE plot, the orange is the top boundary, the gray is the lower boundary. We see that for three-way uncontrolled signalized intersection, we are kind of deviating from those bounds, similarly for the other one. For this one, four-way signalized intersection, we are within the bounds, but for the rest of them, they're not showing a good fit. Therefore, we said that let's develop our own functions using NJ-specific data. We're using the same base SPF given in the HSM. We are using ADT for the minor approach and the major approach and the minor approach, and we have our function like this given in the box here. We have also the major ADT range and the minor ADT range. Similarly, for three-way signalized intersection, which is not included in the HSM, we were able to develop an SPF for this one. Also, four-way unsignalized intersection and four-way signalized intersection. So if anyone would like to find out, for instance, the average number of crashes per year at a four-way signalized intersection, in a rural roadway setting in New Jersey. Just plug in the ADT major on the major approach and the minor approach, and it gives us the predicted number of crashes. And for the segments, the HSM requires that all the homogeneous segments is either equal to 0.1 mile. The minimum length for the homogeneous segments is 0.1 mile. So we had a total of, after data processing, we found out the homogeneous segments, we found out nearly 14,000 segments. And the ones that are 0.1 mile or longer are nearly 6,000. And so we wanted to improve the accuracy of the SPF, so and also the calibration factor. So we only chose the ones that had AEDT station inside the segment. So that kind of reduced our data sample to 679. And the calibration factor was 155, and the coefficient of variation is 0.08, which is within the acceptable boundary. However, when we look at the curve plots plotted against AEDT and roadway length, for roadway length it is within the bound, but for the AEDT it deviates from the acceptable boundary. So we went and used the same data to develop the SPF. As you can see, we're using AEDT and length as covariates, and this is our SPF for the rural two-lane homogeneous segments. Now, these are the results. So this is the first objective of the webinar, showing you the results, demonstrating you the results for the R2 segments in this section. Now, the second part is talking about the inconsistencies in the database, especially in the crash database. As I mentioned in the previous slides, as surprise, so everything that I presented in the previous slides, the results were presented based on the latest version of the safety, the Voyager safety crash database. This was given to us on June 3rd, 2019, covering years from 2011 to 2018, but we use only from 11 to 15 for our analysis, 5 years of data. And when we looked at the data, we find out that the number of crashes per year was lower than what was provided before, because we had a previous set of data, crash data. And the latest version that was given to us towards the end of the project was quite different. And turns out that, as I said before, New Jersey Department of Transportation post-processes the road crash data and geocode the X and Y coordinates. And they increase the filters. So to make it more reliable, they change the filter, and because of that, the threshold, because of the stricter threshold, the number of crashes kind of reduced. Using 2011 data, for instance, the previous version that we had nearly 275,000 crashes with X and Y coordinates, and the new version had 234,000. So nearly 16% of the previous version were missing in the new one, and 52% of those missing were at the urban arterials, and 25% of the missing crashes were on divided roadways. So you see that because the crash location is a very incomplete part of the crash database, as it is in many states. These are approximated values. It can change many things. Using a lot of data, a lot of time for manual data extraction, for instance, to get one information, and one small difference in the crash database can change everything. So it kind of annuls your manual labor. So we said, okay, let's compare what if we had the previous version, not the new version. What if we had the previous version for our analysis, and then see how that will have impacted the calibration factor. So now here I'm showing not only the R2 segments and intersections, but also all the facilities that we did in the project. So you can see that the calibration factor changes considerably. If we had the data set before, the calibration factor would have been found as 1.8. Now our calibration factor is 1.55. Now for some of them, for instance, for here, it's not too much of a difference, but for others, for instance, for the rural multilane segments, we have 1.7 compared to 1.1. So it makes there's a huge difference between the calibration factors. So that kind of brings me to my conclusions, the overview of the project. There are many other data required by the HSM that are very hard to extract and find. So, and also, it is expected that many other DOTs will try to calibrate HSM SPFs or develop local SPFs, or the ones that already did this process will update the existing ones as new data become available. So for each of this process, there is a time spent and manual labor spent. So novel data extraction methods must be used to minimize this time and effort, and also increase the accuracy of the data extracted for both new projects and for recalibration, redevelopment projects. And as I said, as I mentioned in the previous slide, no matter how accurate all other data are, no matter how much time you spend extracting horizontal curvature data or number of left turn, right turn, the accuracy of crash data impacts directly the results, not only the calibration but also the development results. So therefore, at the end, we need accurate crash data. And that's the bottom line. And one of the other things that we found out is that this process requires a significant expertise, not only computer programming, but also data mining and many other things. And most safety experts are not very well versed in this area, and they require automatic updating of calibration and development results. So 3 years or 4 years from now, when new crash data become available, they need to recalibrate or redevelop these results, and the same research team might not be available. So there has to be some kind of a automatic way of recalibrating or redevelopment of the functions. So that will be hopefully the implementation phase of this project, where we are presenting an automated way of doing this, at least for the calibration part. This figure is what we came up with. We have the straight line diagrams, and that also gets updated every 2 to 3 years. So they have tables within the same format. We can read this automatically and then do the segmentation process to find out the homogeneous segments and intersections. We can use the traffic volume data to feed into the intersections, and the crash data feed into the segments and intersections, and then find out if manual data extraction is required. And then the third part is we can do the calibration process and automatically find out the calibration factors for a given facility. So hopefully this will be very useful for New Jersey Department of Transportation, and they can update the calibration factors, hopefully, and also hopefully the SPFs that we developed without minimal effort for them. And this concludes my presentation.
We actually have 2 questions in the wings right now. from Amy Jefferson at NJTPA.
I think the question is essentially, what do you do can you describe the data in the database? Was any geocoding necessary, or was the database that you had from NJDOT fully listed with the milepost?
Yeah, so I mean, if the one, I'm sorry, go ahead, Dr.
Yeah, I think this is like a perennial question, like how do you go from SRI to milepost? And actually, this is something that we have done previously, and I think we've done it in this project, and we shared it with NJDOT, the code. I'm correct, Bekir. No, I mean from like SRI to MP. How do you go to milepost? SRI to milepost, basically.
Actually, the GIS database that is available online has both the SRI and the milepost. So it is available. So we didn't have to do much so when you click on a given link on GIS, it shows you where the SRI and the other start and end milepost each and every link in the states.
Bekir, I think this is. I think the question is more about the way the crash data is recorded itself, though. In terms of, the mapping of crash data from the crash incidents to the exact.
Okay. Yeah, so the Voyager crash database has the X and Y coordinate and also the SRI and milepost. But if that's what we tried to say in the last slide, a couple of slides towards the end, most of the SRI and milepost information are missing. So actually, DOT geocodes it beforehand and gives us a database, but still there are some SRI and mileposts are missing. So we generated using a C programming code that we developed, and then we assign using the X and Y coordinates, and we find the SRI and milepost of each crash. So we were able to restore.
So we have a code, and then we shared that code with NJDOT. Chris Sajak has the code.
So I can perhaps here show you where that is. We had that took a long time to right here. This is exactly what Amy was asking. So this is the slide where we showed the missing SRI and mileposts. Although we have the X and Y coordinates, some of them did not have SRI and mileposts. So we use this methodology, and it took a long time, but it was a one-time process, and we were able to get the SRI and mileposts.
From the XY coordinates.
Exactly.
Of course, you're assuming that the XY coordinates are correct. So
exactly. So that comes from DOT. They use a geocoding process to get the X and Y coordinates. They use cross street names and stuff like that to find out the X and Y coordinates.
We actually have another question that was emailed to me. So since calibration of factors is so challenging, would using non-state specific factors still have value in applying as a first cut analysis?
Non-states? What is that?
I guess this is referring to the more general factors. So like you were using New Jersey.
Yeah, the calibration factors are, so the HSM has a certain SPFs for base conditions. Now, if you're using it in another state, you have to calibrate it using the crash data from that specific state because that changes from one state to another, even within the state. For different counties, it might change. So there are no fixed calibration factors, if that is the question. But you cannot really take the.
In like again, just to recap, SPF is developed using nationwide data, so definitely it has some non-New Jersey effects. So that's why you have to recalibrate or you have to redevelop New Jersey specific functions. So that's what one of the research questions, like, are they really different or are they really similar? So
any more questions from the participants? For one more question.
Sure.
Absolutely, I have all the time.
How close is this methodology to with regards to plan for safety? Or plan for safety?
Plan. Of course, plan for safety is something I think that was developed. I don't know who's asking the question. Is there a name for the person?
Yeah, Chaitanya Pathak. Five?
Yeah, I mean, I think Plan for Safety was being developed when I was at Rutgers, but um, I don't know how it's being used. I mean, it's not widely made available. And when we did this for Bureau of Safety at NJDOT, they did not ask us to compare it with Plan for Safety. But Plan for Safety, as far as I remember, it's a like a GIS based tool, so it doesn't have and shouldn't have its own methodology. I mean, this is a national methodology that was developed by NCHRP and USDOT. So what we are using actually is what actually NJDOT is using for doing safety analysis in their Bureau of Safety. I don't think this is what is going on here has anything to do with Plan for Safety. So Plan for Safety is just a kind of a tool for visualizing and looking at the crash data, as far as I know. If not, maybe more happened since I left, but this was never brought to our attention by NJDOT. So Bekir, just correct me if I'm wrong. So this basically—
Yeah, you're right. I mean, the last time I remember when I was at Rutgers, Plan for Safety was used to visualize crash data.
And again, we work with the safety people at NJDOT, and it was never brought to our attention because, again, this is. I mean, again, this methodology, this SPF functions, can be incorporated into Plan for Safety. And actually, one of the deliverables of our project is to add these SPFs into the spreadsheet that NJDOT is using for their safety analysis. So Bekir, maybe you can say a few things about that, because that was the last part of our project.
Yeah,
How this
absolutely. Now, if my voice doesn't break up, I'll just try to do it as much quickly as possible. Now, that's what I wanted to talk in the last slide. This requires a lot of expertise, even to use the calibration factors or the developed SPF. So, because in day-to-day analysis of the safety experts at DOT, they use a certain spreadsheet, the HSM spreadsheet. Now, if you want to bring in a new SPF, a new function in a different form, you have to modify the spreadsheet. So that requires a lot of time, and a lot of collaboration between the research team and the NJDOT experts. For certain facilities, they want to use, for instance, the calibration factor, but for certain facilities, they want to use the New Jersey specific SPF. So, I mean, it's not sufficient just to come up with the result. You have to kind of make it usable for the safety bureau. If it's not being used, it is just being forgotten. I mean, that's the unfortunate
but I mean, again, this is not, I mean, again, as far as I know, because again, Plan for Safety is something that wasn't made available to us.
Mm-hmm.
This is not like instead of Plan for Safety. This is a national.
No.
It's a national approach to do safety analysis, part of HSM, and we were tasked to work with that. So if anybody wants to know more about HSM and how each function is updated, calibrated or re-estimated, it's in the report, but it follows very tightly the procedure of HSM, basically. So you need to read HSM, understand what it is, and then be able to use these functions actually. And by the way, I mean, NJDOT, I cannot cite the names, but NJDOT Bureau of Safety is very heavily involved in using HSM. I mean, they're experts in NJDOT using HSM, so they know very well, and they're using it on a daily basis. So that's why the project was, I think, quite successful, because we were able to talk to them and they understand every detail of these SPFs. So in that sense, NJDOT is very well versed in HSM and this safety performance functions. So
there's a new comment from Christine. She says that it's being used. I think she's referring to the calibration factors. She says, I'm using these new calibration factors in my HSM analysis.
Yes.
So,
and again, I mean, that's the whole idea. I mean, to use these, and then again, I mean, one key question is that maybe 3 years from now you need to update them, but we have also the procedure how to update them. It's not automated, but there's a procedure. So, and again, we'll be glad to talk about that. And also, I mean, one thing is, again, we have to check with DOT, but we created a shared folder with all the unified database. So again, anybody who wants to try different things, I think that database is available, and we would like people to use that unified database.
Okay.
Yes.
Thank you very much for that. So I think that's a wrap. Thank you again, Dr. Bartin and Dr. Osby. Thank you.
Thank you very much.
Members.
Thank you, John.
Thanks for the good questions. And again, this project was a result of work sponsored by NJDOT. Thanks everyone for joining us today.